Now let's look and see how we're going to do subtraction. We noted that in our 32-bit floating point binary representation, the very first bit represented the sign. So if the first bit was a 0, then we had a positive number. If the first bit was a 1, we had a negative number. So I've redone just the first 6 numbers here, and you'll note that 0 can be written in 8 bits like this, and then 1 is these 8 bits, and then we've got 2, 3, 4 and 5. Now if we were to put a 1 in front of this here, then we could say that this number here would be -1, -2, -3, -4, -5, and we would also have an extra number here which we could call -0. So in effect this is what we do in our 32-bit floating point representation. And we can add these numbers together and we can get another 32-bit floating point representation. But what happens when we try to subtract them? So let's take two of the numbers. We're going to look at 5 minus 5. So in order to get 5 minus 5, what we do is we write 5 plus the -5. So one of them gets negated and we do the normal addition, and that should give us a value of 0. So we can take our number 5, so that's our number 5 here, and we can take our -5, and that would be our -5 here, and we can add both of them together. Now I won't talk through the addition, the addition is quite straightforward, and you can see here that the final answer is actually going to be, well, this 1 here tells us it's a negative, and the number is going to be 1, 2, 4, 8, so that's 10, so we're going to get -10. So 5 plus -5 should give us a 0, but we're getting -10, so this doesn't work. We can't just simply add these numbers together. We're going to have some other operation in order for us to do the complete subtraction and get the right answer. Now, in order to get a 2's complement representation, first of all we negate the number and we add 1. So let's do just the first part of this. We'll do the negation. So we've got our original numbers here written with the sign here represented by the first bit. So this is our -5 all the way to -0 and our 0 up to 5. Now whenever we 1's complement it, what we do is we leave the sign bit as it is. Okay, so the first bit here just remains the same, but then we invert the rest of the bits for the negative values only. Okay, so that means that this number here, for example, will become the 1 remains as the 1. These get inverted, so they all become 1s, and this gets inverted, so it becomes 0, 1, 0. So that's 0, 1, 0. So that represents -5, -4, and all the way up to 5. So let's add these two together and see whether we get the right answers. So we'll try 3 of them. We're going to 5 plus -5 equals 0. Well, this is a 5 here, so we can just pick out our number 5, that's it down here, and this is the -5 up here, and when we add them together we get this answer here. Now this answer here isn't in fact the value -0 in 1's complement, so it's not quite right. We're wanting to get the value of 0, we'll get a value of -0. Now we can do the same with these other 2's. We've got the 5 plus -2. Again, we grab the 5, which is down here, and we grab the -2, which is this one here, and whenever we add them together we get this value here. So this answer here is the answer 2. Now the correct answer should be 3, so we're 1 out. Now if we try the same thing with the 5 plus -3, you'll see we get the answer 1, and the correct answer should be 2. So again, we're 1 out. So this gives us a possible solution here. We could take this 1's complement. In order to get the correct answer, we could just add 1 onto it, and that would give us the correct answer. So for example, we could add on the 1 here and it go from -0 to 0. We could add on the 1 here, it go from 2 to 3, add on the 1, it go from 1 to 2. So let's see that in the next page. So now down this column here, I've written the 1's complement representation from -5 up to 5. Now we said that in order to get the 2's complement, what we have to do is add 1 onto these. So you'll look at one for example, say that minus 2 ends in 0, 1. So whenever I add 1 on to it, the minus 2 will end in 1, 0. So we go to the minus 2 here, and you can see it's ending in 1, 0. So I've simply added 1 to each of these in order to get the 2's complement number here. And you can see the 2's complement will now run from minus 6 over to 5. So if we were to go through these same subtractions again, we would have 5 plus minus 5. So we'd be taking our number 5, which is this normal number here, what we'd normally get, 5, so this one here, and we would be adding on the negative 5. So the negative 5 is now the 2's complement negative 5, which is this one. So whenever we add these together, we actually get the number 0, so it does work. Now you can check the other two as well. We have the 5 and the minus 2, and you can check the values, and you'll see that each of these work. So it means that we can get the correct answers whenever we use this 2's complement. So let's see what happens whenever we get an answer which is in fact a negative answer, because each of these you can see are 5 minus 2, which is a positive 3 and a positive 2, and you can see that the answer that we get is just a normal binary number. So this is just the normal binary number 2, and that's the normal binary number 3. But it's slightly different whenever we get a negative answer. We're going to get the 2's complement number, which are these numbers here. So let's say we do this example here, where we've got 3 minus 5. So that's going to end up with a negative number. So it's 3 plus minus 5, which is equal to minus 2. So this is the number for 3, which is the 2's complement number, which is exactly the same as the normal binary. And this is the number minus 5 in 2's complement. And when we add them, we get the number minus 2. So this is the number minus 2. Now note, this answer here is in 2's complement. So if the answer is negative, then we've got this 2's complement representation. But if the answer was positive, the 2's complement representation would just be exactly the same as the normal binary representation. And we've already seen that whenever we looked at the table here, for instance. You can see that this is a 2's complement representation for positive numbers, and they're exactly the same as just a normal binary. Whereas the negative answers for a 2's complement look different from the normal binary. They are in fact 2's complement. So what we want to be able to do is just have a pure binary representation. So there's two options that we can do, and the top one here we aren't actually going to use. We're going to use the bottom option here, but we'll talk through both of them anyway. So what we can do is we could do this subtraction as we see here, and we can get the 2's complement negative number. We can convert this back to a positive number by inverting it. So we can take this number here, that's just a copy of it, we can invert it, and then we can add 1 to it, and that's going to give us back our pure binary representation. And we can take a note that this is going to be the magnitude of the answer, or the absolute value of the answer, and we know that the sign is going to be negative because this was in fact a 2's complement representation, and we know it's negative because of this 1 here. So that's one option. Now the alternative option is that we can actually compare the two numbers that we're going to perform the subtraction with. So for example, we're looking at the numbers 3 and the numbers 5. And what we can do is we can find the smallest number. So in this instance, the smallest absolute number is the number 3. So what we can do is we can ensure that we always take away the smallest number from the largest number. That'll always ensure that we always end up with a positive value. So for instance here, we could look at this one here, we could figure out which one is the smallest. And then we can, if we have to, we can swap them round about so that we could have, instead of 3 plus minus 5, we could have 5 plus minus 3. We'll still get an answer of 2. So the magnitude of the answer will still be correct. And the beauty here of it is that whenever we look at the representation of this here, the representation gives us a positive 2's complement, which is just exactly the same as our binary answer. So we get our normal binary answer here. And of course, we can also take a note that it is in fact a negative number. And we know it's a negative number because we've had to swap these round about in order to ensure that we ended up with the correct format here. So we'll have a note of the fact that it's a negative, and we'll also have the absolute value. So this is the option we're going to use here. Now don't worry too much if that sounds a bit confusing. Whenever we go through and look at it in the Excel spreadsheet, you'll see it happen in the Excel spreadsheet. And this is a much neater option for us to work through in our floating point unit adder and subtractor design. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.